Welcome to the Sleepy Scholar. Settle in wherever you are. Let the weight of the day begin to loosen its grip, one muscle at a time, from the crown of your head, down through your shoulders, down along your arms, into your hands. There is nowhere you need to be tonight. There is nothing you need to solve. There is only this quiet voice, and a very large and very old idea. And all the time in the world to turn it over slowly, the way you might turn a smooth stone in your palm in the dark. So let me tell you a story about the sky. Not the sky as it is tonight, with its scattering of familiar stars, but the sky as it will be a very, very long time from now. Imagine, if you will, an astronomer. Not a human astronomer necessarily, just some patient, curious mind, somewhere out in the deep future, on a world orbiting a star inside a single island of stars. This astronomer is careful. This astronomer is honest. This astronomer builds telescopes, measures light, writes down numbers, checks the work, and checks it again. Everything you would want a good scientist to be, this one is. And one night, that astronomer points the finest instrument their civilization has ever built up at the darkness overhead and begins to map the universe. And here is what they find. They find their own island of stars, a great slow wheel of suns and gas and glowing dust turning through the void, and around it, in every direction they look, they find nothing. Not sparse galaxies. Not faint smudges of distant light, nothing at all, just black. A perfect, seamless, unbroken black, going on forever, with their single island of stars floating alone at the center of it like the last lit window in a sleeping city. So this careful astronomer does what any careful astronomer would do. They measure what they can see. They study the motions of the stars in their island. They find that everything is stable, orderly, gravitationally bound, going nowhere in particular. There is no sign of expansion, because there is nothing left in the sky to expand away from them. There is no distant light stretching and reddening, because there is no distant light at all. And so, drawing the most reasonable conclusion the evidence allows, this astronomer writes down the truth of their cosmos as they can best determine it. The universe, they conclude, is a single island of stars. It is small, it is static, meaning it is not growing and not shrinking, and it is eternal, unchanging, always having been more or less as it is now, always going to be. One lonely, permanent island in an infinite and empty dark. And every single word of that conclusion is wrong. Not because the astronomer was sloppy, not because they made a mistake in their arithmetic. They did everything right. They used good instruments and sound logic and honest measurement. They reached a false picture of the whole universe using the very same method that we use to reach a true one. The difference between them and us is not intelligence, and it is not care. The difference is only this. They were born too late. By the time that astronomer opened their eyes, all of the evidence, every last clue that would have told them the real shape of things, had already quietly slipped away. The universe erased its own history and left them holding a sky that lied. This is not a fable. This is a real prediction, worked out in real physics, published by two physicists named Krauss and Robert Scherrer in a paper from 2008 with a title that is somehow both dry and chilling at once. They called it The Return of a Static Universe and the End of Cosmology. And what they showed, using nothing more than the best understanding we currently have of how the universe behaves, is that the sky is slowly, patiently going dark. That the far future holds a cosmos that will look almost entirely empty, and that anyone alive to see it will have no way at all, of knowing the extraordinary truth of where they came from. So let that idea sit with you for a moment, softly, the way you'd let a candle flame settle after someone walks past it. The universe is going to hide itself, and it has given us a number for how long we have to look before it does. It is a strangely, almost unsettlingly precise number, and we will get to it, and I promise it is going to sound both impossibly far away and, in the grand scheme of things, oddly soon. But first, let me ease you into the shape of the whole idea, because everything tonight rests on one strange fact that took the sharpest minds on Earth by complete surprise less than a single human lifetime ago. Here is the thread I want you to hold loosely as we drift through this. We are not the ignorant ones. That is the twist, and it runs against everything you might expect. When we imagine people who don't understand the universe, we usually imagine the past. People long ago, squinting at the stars, guessing at gods and crystal spheres, not yet having the tools to know better. We think of ourselves as somewhere in the middle of the story, with the ignorant behind us and the enlightened ahead. But it is the other way around. We happen to have opened our eyes during a rare and narrow window. A window when the universe is still legible, still full of clues, still telling its own story out loud across the sky. And that window is closing. Not tonight. Not for an unthinkable stretch of time. But it is closing. Slowly and certainly. And the people of the far future will live on the other side of it, in the dark, with the book of the cosmos torn out page by page, until only one page remains. We are, right now, in what cosmologists have started to call, quite literally, the golden age of cosmology. And golden age is not a compliment we are paying ourselves. It is a warning about timing. Hold on to that thought. We will come back to it, again and again, and it will mean more each time. Now, to understand why the sky goes dark, we have to go back to the moment we found out the universe was doing something nobody expected it to do. And to feel how big a surprise it was, you have to understand what everyone assumed beforehand. For most of the 20th century, once we had accepted that the universe was expanding at all, which was itself a hard-won and fairly recent idea, the natural next question was simple. The universe is flying apart. Everything is rushing away from everything else. So what is that expansion doing over time? And the obvious, sensible, almost common-sense answer was that it must be slowing down. Think of throwing a ball straight up into the air. It leaves your hand fast, and then gravity, patient and relentless, drags on it, and it slows, and eventually it stops rising. The universe seemed like it should be the same. All the matter in it, all the galaxies and gas and dark matter, all of it pulling on all the rest of it through gravity, should be acting like a great cosmic break. The expansion should be coasting to a gradual halt, decade by billion-year decade. The only real question, people thought, was whether there was enough matter to eventually stop the expansion entirely and pull everything back together, or whether it would just keep drifting outward forever. Slower and slower and slower. Either way, the expansion was surely losing steam, that much felt certain. So in the 1990s, two separate teams of astronomers set out to measure exactly how much the expansion was slowing down. Two teams, working independently, sometimes as rivals, chasing the same beautiful and difficult measurement. One was called the Supernova Cosmology Project, led by a physicist named Saul Perlmutter. The other was called the High-Z Supernova Search Team, led by Brian Schmidt and Adam Rees. And to do this measurement, both teams needed a very particular kind of tool. They needed something out in the depths of space that would let them measure enormous distances precisely. They needed what astronomers call a standard candle. Let me unfold that phrase for you gently, because it is a lovely idea and the whole discovery hangs on it. Imagine you are standing in a wide field at night, and scattered across it are hundreds of candles, some near, some far. Now suppose you knew for certain that every single one of those candles was exactly as bright as every other, the same identical flame, the same true brightness. Then just by looking at how dim or bright each one appeared to your eye, you could tell how far away it was. A candle that looks faint must be far. A candle that looks brilliant must be close. Because you already know their true brightness, the apparent brightness becomes a measuring tape. That is a standard candle, something whose real brightness you know in advance, so that its dimness tells you its distance. And nature, it turns out, provides a nearly perfect one. It is a specific kind of exploding star called a Type Ia supernova. Without getting tangled in the details, this particular kind of stellar explosion happens under such consistent conditions that these supernovae all blaze up to very nearly the same true brightness, every time, all across the universe. They are among the brightest events in the entire cosmos, bright enough to be seen from billions of light-years away, briefly outshining whole galaxies. So they are exactly the candle you'd want. Rare, brilliant, and reliable. Find one in a distant galaxy, measure how dim it looks, and you have measured how far away that galaxy is with real confidence. And because the light from a very distant supernova has been traveling for billions of years to reach you, you are also, in a sense, looking back in time, seeing how the universe behaved long ago. Measure enough of these at different distances, at different depths into the past, and you can reconstruct the whole story of how the expansion has changed over cosmic history. That was the plan. That was what both teams were hunting for, night after night, in the faint flares of dying stars halfway across the visible universe. And then the data came in, and it made no sense. The distant supernovae were too dim. That is the whole thing right there, in 3 plain words. Too dim. When both teams looked at the most far-off supernovae, the ones whose light had travelled the longest, they found them fainter than they should have been. Fainter than they would be if the universe had been expanding and gently slowing down all this time. And too dim means too far away. Those supernovae were farther out than a decelerating universe could account for. Something had carried them out beyond where the old, sensible, coasting to a stop picture said they should be. There is only one thing that carries them out there. The expansion of the universe was not slowing down. It was speeding up. It was accelerating. The cosmic break everyone had assumed was there, the gravity of all the matter pulling everything gradually to a halt, was not winning. Something was overpowering it. Something was pressing outward, pushing space itself to expand faster and faster as time went on, flinging the distant galaxies out beyond all expectation. Now, I want you to feel how strange this was to the people who found it, because they did not want to believe it. This was not a result anyone had gone looking for. Both teams, independently, kept trying to find the mistake. They checked whether the distant supernova might just look dim because of dust in the way, dimming the light like fog around a street lamp. They checked whether these ancient supernovae might somehow be a slightly different, fainter kind of explosion than the nearby ones. They turned the data over and over, hunting for the error that would make the universe sensible again. And the error never came. Two rival teams, using different supernovae, different methods, different assumptions, arrived at the same impossible answer. The universe is not coasting to a stop, it is accelerating. The ball we threw into the air is not slowing down. Somewhere near the top of its arc, it began, gently and impossibly, to rise faster. This was 1998, within a human lifetime of right now. Many people alive today were already grown adults when we did not yet know the most important single fact about the fate of the entire universe. And the discovery was so profound, so completely unexpected, and so thoroughly confirmed that in 2011, Saul Perlmutter, Brian Schmidt and Adam Rees were awarded the Nobel Prize in Physics for it. For finding the thing nobody was looking for. For catching the universe in the act of accelerating. So then the obvious question, the one that has occupied physicists ever since, is simply this. What is doing the pushing? What is this thing that overpowers the gravity of every galaxy in the cosmos and drives space to expand faster and faster? And the honest answer is that we do not fully know. We do not know what it is. Not really, not in the way we understand what a proton is or how a star burns. But we have measured it carefully from many directions, and we have given it a name that is really more a confession of ignorance than an explanation. We call it dark energy. Let me be clear about how much of it there is, because this is one of those numbers that ought to rearrange how you see your own reality. Dark energy is not some minor ingredient, some faint extra spice in the cosmic recipe. Add up everything in the entire universe, every star, every planet, every galaxy, every cloud of gas, every human being, every atom of ordinary stuff you have ever seen or touched. All of that, all the ordinary matter, comes to only about 5% of the universe, a 20th. The rest is invisible. About 27% is dark matter, a different mysterious thing, some unseen substance whose gravity holds galaxies together, and we will let that one rest tonight. Because it is not our story. Because the largest share, the great majority, about 68% of everything, more than 2/3 of the entire energy content of the cosmos, is dark energy, the stuff pushing space apart. The thing we did not know existed a single human lifetime ago is by far the dominant feature of the universe. We are living inside a reality that is mostly made of something we cannot see, cannot bottle, and cannot fully explain, and it is that something that will, in the fullness of time, empty the sky. These proportions, by the way, are not loose guesses. They come from exquisitely careful measurements, including from a space telescope called the Planck satellite, which spent years mapping the faint heat of the early universe in extraordinary detail. 5% ordinary matter, 27% dark matter, 68% dark energy. That is the accounting of everything. Now, what is dark energy actually like in its behavior? Here is where a very old idea comes quietly back into the story, an idea from Albert Einstein from all the way back in 1917. When Einstein first wrote down his equations describing how gravity and space and time all fit together, he found that they seemed to describe a universe that could not sit still. It wanted to either expand or collapse. And at the time, everyone, Einstein included, believed the universe was static, fixed, eternal, unchanging, exactly the picture our lonely future astronomer will someday wrongly believe. So to hold his equations still, to keep the universe from moving in his mathematics, Einstein added a term, a little mathematical counterweight. He called it the cosmological constant, and physicists write it with the Greek letter lambda, that little standing figure like a legless capital A. The cosmological constant was, in effect, a kind of pressure built into empty space itself, a tendency for the vacuum to push outward, exactly enough to balance gravity's pull and keep everything from collapsing. And then the universe turned out not to be static after all, and Einstein, so the story goes, called the cosmological constant his greatest blunder and set it aside. For decades it sat in the drawer, an embarrassing leftover, a fudge that turned out to be unnecessary. Except when we discovered in 1998 that the expansion was accelerating, that old discarded idea fit the new data almost perfectly. Dark energy behaves, as far as we can measure, exactly like Einstein's cosmological constant. A pressure woven into the fabric of empty space, pushing outward. Physicists have a technical way of describing this behavior with a quantity they call the equation of state, written as the letter W, and for a true cosmological constant, that number should be exactly -1. And when we measure dark energy across every method we have, we get a number that is right around -1. As close to -1 as our instruments can determine. The blunder was not a blunder. It was a prophecy Einstein didn't know he was making. And here is the single most important consequence of dark energy behaving like a true cosmological constant, the property that seals the fate of the far future sky. And I want to say it slowly, because everything downstream flows from it. A cosmological constant does not dilute. It does not thin out. Think about ordinary matter for a moment. As the universe expands, the galaxies spread apart, and any given region of space gets emptier. The matter gets more and more diluted, more spread out, thinner, and so its influence weakens over time. That is what you'd expect of anything. Spread it over more space, and there's less of it in any given place. But dark energy, if it is truly Einstein's constant, does not behave that way at all. It is a property of space itself, so when the universe expands and makes more space, it does not thin the dark energy out, it makes more dark energy. Every new cubic meter of space that expansion creates comes pre-filled with the same amount of this outward pressure as every other cubic meter. It never weakens, it never fades. As the eons pass and the universe grows, everything else, all the matter, all the galaxies, all the light, thins and dims and dilutes toward nothing. But dark energy holds perfectly steady, undiluted, patient, and because everything else is fading while it alone remains, it comes, inevitably, to dominate, to rule, to decide the ending. The thing that never thins out always wins in the end. That is the quiet engine underneath this entire story. So already, without going a single step further, you can feel the shape of the fate. A universe with a constant, undiluting outward pressure baked into every cubic meter of empty space, growing faster and faster forever, flinging its contents ever farther apart. And that pressure only ever growing more dominant as everything else fades. This is not a universe that coasts to a peaceful, crowded stillness. This is a universe that empties itself, that spreads its own contents out past the point of ever being seen again. And that brings me to the first genuinely unsettling thing I want to leave you with tonight. The first payoff. The first clue that our comfortable picture of the night sky is already, quietly, an illusion. Because you might think, all right, this emptying happens in the far future, 100 billion years from now. It has nothing to do with the sky I see tonight. The galaxies are still out there. The deep telescope images are still full of them. Thousands upon thousands of galaxies in a single patch of sky, no bigger than a grain of sand, held at arm's length. Surely all of that is still real, still reachable, still ours. But it is not. And here is the fact that ought to give you the gentlest chill as you lie there in the dark. Of all the galaxies you can see, right now, in the deepest and most powerful telescope images ever taken, the great majority are already gone. Not gone in the future. Gone now, in every sense that matters. Astronomers have worked this out carefully, physicists like J. Richard Gott and others, like Abraham Loeb and his colleagues, running the numbers on how far a signal could travel from us across an accelerating, expanding universe. And the answer is that somewhere around 94 to 97% of the galaxies we can currently see are already beyond our reach forever. 19 out of every 20. If we sent a message today, right now, at the speed of light, the fastest anything can possibly travel toward the great majority of the galaxies glittering in those deep images, that message would never arrive. Not because the galaxies are too far in the ordinary sense, but because the space between us and them is expanding so quickly, and expanding faster all the time, that our light speed message would lose the race. It would fall forever behind the outward rush of space. It would chase those galaxies for the rest of eternity and never, ever catch them. Which means, in the truest sense, that when you look at those distant galaxies, you are not looking at things you could ever visit, or signal, or touch, or affect in any way. You are looking at their old light that left them billions of years ago and has been swimming toward us across a widening gulf ever since, arriving now, tonight, in your eye or in the mirror of a telescope. But the galaxies that sent it are already, in the only sense that counts, across an uncrossable line. They are ghosts. Beautiful, glowing ghosts. Photographs of a farewell that already happened. We are watching light from galaxies that have, for all purposes, already left us, and the light is all we will ever have of them. 19 out of 20. Already gone. And the sky looks so full, so permanent, so densely scattered with light that nothing about it warns you. Nothing about that quiet sea of galaxies whispers that most of them are already goodbye. It is only when you do the arithmetic of the expanding universe, only when you take the acceleration seriously, that you realize the emptying has already begun. It began long ago. We are simply still close enough to the beginning of the process that the sky still looks full. The way a room can still look bright in the first few minutes after sunset, before you notice how much the light has already drained away. So here is where we stand, as this first part of our long, slow story draws its first breath and prepares to go deeper. We have learned that the universe is not slowing down, but speeding up, a fact we discovered only in 1998. From supernovae that came in too dim, a discovery so profound it earned a Nobel Prize. We have learned that the culprit is dark energy, more than 2/3 of everything there is, behaving like Einstein's long-discarded cosmological constant, a pressure in empty space that never thins out and so is destined to rule the ending. And we have learned that this ending has already, quietly, begun. That most of the galaxies in our sky are already ghosts, already past the line, already gone, though their old light still reaches us in this fleeting, privileged now. And we have met, in the darkness of the far future, our lonely astronomer staring up at a black and empty sky, doing everything right and concluding, wrongly, that they live in a small, static, eternal island of stars. We have not yet seen how, exactly, the sky empties itself down to that final blackness. We have not yet seen precisely which clues vanish, or in what order, or why even the faint afterglow of the beginning of the universe will one day become not merely hard to detect, but physically impossible to detect. We have not yet met the one galaxy in all the sky that is moving toward us rather than away, the single companion we get to keep. And we have not yet felt the full weight of the strangest part, which is that we have been fooled by exactly this kind of darkness once before, and not so very long ago, and that the future does not just repeat that mistake. It makes it permanent, and it takes away, forever, any way of ever finding out the truth. So breathe, slow and easy, and stay with me here in the warm and quiet dark. The night is long, and the story is far from over, and there is no hurry at all. Because we have that number to reach, that shockingly precise number for how long the sky has left to tell its story, and to understand it, we first have to understand the strange and beautiful machinery of expanding space itself. The difference between the distances we can see and the distances we can ever reach, and why a galaxy can fly away from us faster than light without breaking a single law of physics. And so, with the fire of the far future still glowing low, and the ghosts of 1,000 galaxies still drifting their old light down toward us through the widening dark, let us go on, slowly, and look at how, exactly, the universe learned to hide. There is a word for what the universe is doing, and it is a word that sounds almost gentle, almost harmless, until you follow it all the way to where it leads. The word is expanding. Space itself is growing. Not in the sense that everything is rushing outward through some larger container, like sparks flying away from a fire into a surrounding darkness. There is no surrounding darkness, no edge to fly toward. The expansion is interior. It is happening everywhere, in every gap between things that are not held together by gravity, in every unbound stretch of intergalactic space, quietly and continuously and without asking permission. The distances between unbound things are simply becoming larger. That is what expansion means. For most of the 20th century, after Edwin Hubble showed that the galaxies were receding and that the farther ones were receding faster, the assumption was that this expansion would slow down over time. Gravity pulls. Everything pulls on everything else, and even across the vast gulfs of intergalactic space, the cumulative gravity of all the matter in the universe was expected to act like a hand laid gently on the shoulder of a running person, not stopping them, but gradually, patiently, reducing their speed. The question cosmologists spent decades asking was not whether expansion would slow, but whether it would slow enough to eventually halt and reverse, whether the universe would one day collapse back on itself in a big crunch, or whether it would coast outward forever, slowing but never quite stopping, thinning and cooling into an endless dark chill. Those were the two options on the table, and both of them assumed the same thing, that the hand on the shoulder was always there, always pushing back against the rush of space. What the two supernova teams found in 1998 was that the hand was not pushing back, it was pushing forward. The expansion was not slowing, it was speeding up. That discovery, which sent those teams back to their numbers again and again in something close to disbelief before they trusted it enough to publish, changed everything. And to understand why it changes everything, why it means that the sky eventually goes dark in the specific, complete, irreversible way it does, you have to understand what kind of expansion an accelerating one actually is. You have to understand the difference between coasting and running away. Think of a ball thrown straight up into the air. If you throw it hard enough, it rises, and gravity tugs it back, and it slows, and eventually it stops climbing and falls. If you throw it harder than a certain threshold, hard enough to overcome Earth's gravity entirely, it escapes, but even then it slows as it goes, losing speed with every kilometre of altitude, gravity's reach growing weaker, but never quite reaching zero. This is the model the universe was expected to follow, a cosmos thrown outward by the Big Bang, possibly fast enough to escape its own gravity, but always decelerating, always losing some of its initial momentum to the collective pull of everything on everything else. What dark energy does is entirely different from merely throwing the ball hard enough. What dark energy does is imagine that instead of gravity gradually decelerating the ball as it rises, there is some other force that grabs the ball once it is high enough and begins to accelerate it upward, faster and faster, so that the higher it goes, the faster it goes. So that its speed does not merely hold steady, but compounds, so that by the time the ball is very far away, it is moving not at the speed it started, but at a speed far beyond that, a speed that grows without limit. That is the kind of expansion the universe is actually doing, and it leads to something mathematically specific and physically dramatic: exponential growth. Exponential is a word that gets used loosely, sometimes meaning merely very fast, but here it has a precise mathematical sense, and the precision matters enormously. When a quantity grows exponentially, it does not just increase, it increases at a rate proportional to its current size. The bigger it is, the faster it grows. The faster it grows, the bigger it gets. The bigger it gets, the faster it grows again. This is the runaway feedback loop that compounding interest exploits, the thing that makes a virus spread from 1 person to 2 to 4 to 8 to 16, without the numbers merely adding up, but instead multiplying. And in the cosmological setting, when dark energy behaves as a cosmological constant, when it has an equation of state parameter u equal to -1, as measurements from the Planck satellite and other instruments consistently find, the cosmic scale factor, the number that describes how big the universe is relative to some reference size, grows according to the mathematical form A is proportional to e raised to the power h times t, where e is Euler's number, approximately 2. 718, the base of natural logarithms, the number that governs all exponential growth, where h is the Hubble constant, that rate of approximately 70 kilometers per second per megaparsec that describes how fast space is currently expanding, and where t is time. As t increases, the exponent h increases, and e raised to a growing exponent does not merely grow, it accelerates without limit. The scale factor does not coast, it runs, and then it sprints, and then it is gone. This is called de Sitter expansion, named for the Dutch physicist Willem de Sitter, who worked out this kind of geometry in the early 20th century when exploring the implications of Einstein's cosmological constant. Einstein had originally introduced that constant, symbolized by the Greek letter lambda, into his equations of general relativity in 1917, intending it as a kind of mathematical ballast to keep his equations from predicting an expanding or contracting universe when he believed the cosmos should be static and eternal. He famously called it his greatest blunder after Hubble's discovery of expansion seemed to make it unnecessary. What the 1998 supernova measurements showed was that the cosmological constant had never been a blunder. It had been, in a sense, correct all along, just for reasons Einstein had not understood. The cosmological constant describes something genuinely strange, a form of energy that belongs not to matter, not to radiation, not to anything you could put in a box or weigh on a scale, but to space itself. Empty space, according to our best current understanding, is not nothing. It has an energy density. And that density, tiny, barely conceivable, approximately 6 times 10 to the power of negative 27 kilograms per cubic meter, does not change as space expands. When you take a volume of space and stretch it, the matter and radiation in that space thin out. There are fewer atoms per cubic meter, fewer photons per cubic meter, because the same number of things now occupies a larger volume. But the dark energy does not thin out. Because it belongs to space itself, when space grows, so does the total amount of dark energy. It is as if every new cubic meter of space that comes into existence brings with it its own small allotment of this strange vacuum energy, seamlessly, effortlessly, with no additional source required. That density, 6 times 10 to the negative 27th kilograms per cubic meter, is so close to nothing that it is almost impossible to feel as a meaningful quantity. To give you a sense of its smallness, it corresponds to roughly the energy of a few hydrogen atoms spread across an entire cubic meter of space. A cubic meter is roughly the volume of a refrigerator. Imagine taking 3 or 4 hydrogen atoms, the simplest, lightest atoms in existence, and distributing their combined energy across the entire interior of that refrigerator, every corner, every shelf, the whole volume of it, and that is approximately the energy density of dark energy, the force currently ruling the fate of the universe. It is not nothing. But it is very, very close to nothing, and yet it rules because it never dilutes. Every other form of energy, matter, radiation, even the kinetic energy of expansion, becomes less dense as the universe grows. But dark energy holds steady per unit volume for as long as its equation of state parameter stays at -1. And as everything else thins and fades, this near nothing that refuses to thin becomes, in relative terms. Everything, currently, dark energy makes up approximately 68% of the total energy content of the cosmos. Dark matter, the invisible gravitational scaffolding around which galaxies organize, contributes another 27%. Ordinary baryonic matter, atoms, stars, planets, gas, dust, everything you have ever seen or touched or are made of, constitutes roughly 5%. 5%. The substance of which all human experience is constructed is a rounding error in the universe's energy budget, and even that 5% is becoming a smaller and smaller fraction as the space between unbound structures grows and dark energy's relative dominance increases. The universe is moving into a future defined increasingly, and then exclusively, by the energy of empty space. The de Sitter regime is not a distant future possibility, it is where we are already heading, and by cosmological timescales, it is arriving soon. Now, here is where the 3 horizons come in, and where a great deal of popular cosmology quietly blurs together things that are actually very different from one another, in ways that matter enormously for the story we are telling. When you hear that the observable universe is about 93 billion light-years across, a sphere of roughly 46 billion light-years in radius, in every direction, you might reasonably wonder how that can be. If the universe is only 13.8 billion years old and light travels at a fixed speed, how can we see things 46 billion light-years away if light has only had 13.8 billion years to travel? The answer is expansion. The universe was smaller when that ancient light departed, and it has been growing ever since. The photons spent billions of years crossing and expanding space, and the points they departed from are now much farther away than the time the journey took would suggest. The 46 billion light-year radius of what we call the particle horizon, or the observable universe's edge, represents the commoving distance to the most remote things whose light has had time to reach us. Taking into account all that expansion along the way, it is the boundary of everything we can currently see, the edge of the shell of information that has had time to arrive. But seeing something is not the same as being able to reach it. And this is where a second, and in some ways more important, boundary enters the picture: the cosmic event horizon. The event horizon sits at approximately 16 billion light-years from us, in commoving distance. This is the boundary beyond which any signal we send today, any light, any information, any influence traveling at the maximum speed permitted by physics, will never arrive. Not because the distance is too great in a simple sense, but because the intervening space is expanding fast enough and exponentially enough that the signal will spend the rest of cosmic history swimming against a current that grows stronger the farther out it goes, and it will never close the remaining gap. Anything beyond the event horizon is, in the most operationally complete sense, gone. Not gone in the sense of destroyed. Those galaxies still exist, still shine, still harbour whatever civilizations they harbour, but gone from us. Unreachable, beyond the boundary of any possible causal contact, now and forever under the standard dark energy model. Between these two, the particle horizon at 46 billion light-years, the edge of what we see, and the event horizon at 16 billion light-years, the edge of what we can ever affect or receive from, sits the third boundary, the Hubble radius, at approximately 14 billion light-years. The Hubble radius is the distance at which the recession speed of a galaxy, due purely to the expansion of space, equals the speed of light. Galaxies beyond the Hubble radius are receding from us at speeds greater than light. Right now, as you listen to this. That sounds alarming and impossible, but it is neither, and the reason why not is one of the most quietly profound things in all of physics. Light speed, as Einstein's special relativity famously established, is an absolute limit on the speed of motion through space. Nothing can move through space faster than light. But what the expansion of the universe involves is not motion through space. It is the expansion of space itself. The galaxies beyond the Hubble radius are not moving through space at faster than light speeds. They are sitting more or less in their own local regions of space, while the space between us and them stretches at a rate that makes the total distance between us grow faster than light can cross it. It is as if you are on one end of a rubber band and a friend is on the other end, and the band is being stretched, not by either of you moving along the band, but by the band itself growing longer. If the band stretches fast enough, the distance between you and your friend increases faster than sound could travel along the band, even if neither of you moves a single step. The sound waves are still sound waves, still travelling at their own speed, still subject to all the ordinary rules of acoustics. The stretching of the band does not break any rule about the speed of sound. It simply outruns the sound geometrically. This is why seeing a galaxy does not mean reaching it. Some galaxies that are currently beyond the Hubble radius, currently receding faster than light, are still visible to us, because their old light, emitted when they were closer and the universe was younger and smaller, has been travelling toward us for billions of years and has already covered most of the journey. That ancient light departed from a point that was, at the moment of departure, within the reachable universe. The light has been making its way to us ever since, crossing the widening space in steady increments, and eventually it arrives, redshifted and faint, but present in our telescopes. We see the ghost of where that galaxy was, not where it is. And where it is now, far beyond the event horizon, receding at many times the speed of light in terms of how fast the spatial distance between us is growing. We will never reach, and they will never again reach us. The observable universe, the particle horizon, the 46 billion light-year sphere, that is the past light cone, the dome of ancient history that we can study and observe and learn from. The event horizon, the 16 billion light-year boundary, is the future light cone, the shrinking sphere of what is still, even now, in physical contact with us. And the Hubble radius, at 14 billion light-years, is the current instantaneous surface where recession exactly equals light speed, which in an accelerating universe is not the outer boundary of what we see, but rather a middle surface inside both the bigger and the smaller of those other two boundaries. Keep those three surfaces distinct, and the whole story becomes clearer. The observable universe is enormous, rich, full of information stretching back nearly to the beginning of time, but most of what it shows us is already beyond our reach. The event horizon is smaller and shrinking in comoving terms, meaning that as time passes, fewer and fewer regions of space remain within the causal sphere. The sphere of things we could still, even in principle, exchange signals with. And in the far future, when exponential expansion has run long enough, that event horizon will have swept past essentially everything, and all that remains within it will be the bound local systems, our solar system, our galaxy, our small gravitational family. It is worth pausing here to feel the weight of the Hubble radius number for a moment. 14 billion light-years. Galaxies beyond that line are receding faster than light right now, this moment, as the universe goes about its quiet business while you listen to this in the dark. And yet we see them. We see their light, because that light is old, because it was emitted when they were closer, because it has been journeying toward us long enough to have covered the expanding ground between departure and arrival. But those galaxies cannot now send us any new information that will ever reach us. The light they emit today is already racing into a headwind it can never overcome. We are receiving their old letters. No new ones will come. The analysis by J. Richard Gott and others, and by Amos Ory and Abraham Loeb, estimated that the fraction of currently observable galaxies that are already causally disconnected from us, already beyond the event horizon, already sending no new light that will ever arrive, is somewhere between 94 and 97%. Nearly all of them. The sky you see through a telescope, the deep field images showing thousands of ancient glowing points, is almost entirely a gallery of irrecoverable past. We are not looking out at a universe we inhabit in any interactive sense. We are looking at a record, a fossil record, an archive of light from places that have, for all practical purposes, already departed. This is the first layer of darkness, not the darkness that will come in 100 billion years. The darkness that is, in a real sense, already here, hidden behind the brightness of ancient light. And dark energy, this near nothing, this few atoms worth of energy per refrigerator volume of space, is why. Because it never dilutes. Because every increment of expansion it enables makes the space slightly larger, which makes the rate of expansion slightly higher given the same energy density, which makes the space larger still. This is the compounding, the exponential character, the runaway that de Sitter geometry describes. In the early universe, when everything was packed together and radiation and matter were densely concentrated, gravity dominated. Expansion decelerated then, just as the earlier cosmologists expected. But as the universe grew and matter thinned, as the atoms spread out, as the radiation stretched and cooled, as the gravitational influence of all that matter diluted across ever larger volumes, dark energy's fixed density began to catch up, and then to surpass, and then to dominate. The crossover, based on current measurements, happened roughly 5 billion years ago, around the time our own solar system was beginning to form from a collapsing cloud of interstellar gas. The universe was already accelerating when Earth came into existence. Now, the natural question, the one that the story requires before it can move forward, is what survives. If space is expanding exponentially, if the event horizon is sweeping outward past galaxy after galaxy and sealing them away forever, what does dark energy leave behind? The answer is both reassuring and, in its own quiet way, melancholy. Gravity wins locally. Always, dark energy does not pull things apart from within, it governs the space between unbound systems. The operative phrase is unbound. Things held together by gravity, by the mutual pull of mass, are not pulled apart by dark energy, at least not in the standard cosmological constant scenario with W equal to -1. Your body is not being ripped apart. The Earth is not being pulled away from the Sun. The Sun is not drifting free of the Milky Way. These are gravitationally bound systems, and within them, gravity's local strength vastly exceeds any influence from the slow, diffuse push of dark energy. The expansion is not tearing apart what is already tied together. It is only widening the gaps between things that were never tightly enough tied. What this means on the largest relevant scale is that the local group, the gravitationally bound family of galaxies to which we belong, will remain intact. The local group contains more than 80 known member galaxies, though most are small dwarf galaxies orbiting around the two dominant ones. Those two dominants are the Milky Way, our own roughly 100,000 light-year wide spiral, and the Andromeda Galaxy, known to astronomers as Messier 31, a somewhat larger spiral galaxy located approximately 2.5 million light-years away. The third significant member is the Triangulum Galaxy, Messier 33, smaller than both, but still a substantial system in its own right. Together with their attendants, the local group spans roughly 10 million light-years and contains a combined mass estimated somewhere between 2 and 5 trillion times the mass of the Sun. And this whole family, all 80-plus members, is decoupled from the Hubble flow. They are not being carried apart by expanding space. They are, instead, gravitationally bound to one another, orbiting and interacting in a cluster that has essentially opted out of the universe's expansion at the local level. The Virgo supercluster, the larger structure in which the local group sits as a small outlying member, is a different matter. The supercluster itself is not a gravitationally bound unit in the same strong sense, and while the local group is safely bound, the broader supercluster is not fully cohesive against the pull of expansion. Beyond the gravitationally bound core systems, the cosmic expansion wins, and it will continue to win more thoroughly as time goes on. What the local group gives us, what the story says we get to keep, is essentially one merged island of stars, eventually, after enough time has passed. The Milky Way and Andromeda are not merely neighbours, held at a respectful distance, minding their own business and exchanging only light. They are approaching each other. Andromeda is one of the very rare large galaxies in the sky that is blue-shifted rather than red-shifted. It is moving toward us, not away, at a speed of approximately 110 kilometers per second. While virtually every other galaxy we observe is retreating, carried outward on the general expansion of space, Andromeda is coming. This is because it is gravitationally bound to us, because it is not being carried by the Hubble flow, because its own peculiar velocity, its actual motion through space relative to the local standard of rest, is directed inward toward the Milky Way. It is the exception that illuminates the rule. To see a galaxy blue-shifted in a cosmos of redshifts is to see gravity winning visibly against the background hiss of expansion. And it is a preview of what is coming, cosmically, in our own backyard. In roughly 4 to 4.5 billion years, the Milky Way and Andromeda will begin to collide. Not collide in the catastrophic sense that sounds immediate and violent, because the space between the individual stars within each galaxy is so vast that almost no actual stars will physically crash into one another. The collision is less a crash than an interpenetration, a long, slow gravitational dance that will take billions of additional years to fully play out. The two galaxies will pass through each other, swing out on wide arcs, return, merge more deeply on the second pass, and gradually, over a span of billions of years after first contact, settle into a single merged system, an elliptical galaxy, roughly spherical, built from the combined stellar populations of both the Milky Way and Andromeda. Cosmologists have given this merged future galaxy an informal nickname, Milkomeda, or sometimes Milkdromeda. It is a portmanteau that carries a certain wry tenderness, a recognition that these two enormous star cities, each hundreds of billions of stars strong, are already on cosmic timescales on a collision course that ends in a permanent union. The Sun will likely survive this merger, though its position within the merged galaxy will be different from where it is now, probably somewhat farther from the center, in some outer arm or halo of the new elliptical, continuing to age and eventually die, as it was always going to do, regardless of galactic politics. Milkomeda, along with the smaller members of the local group, will eventually coalesce into essentially one entity, one island, one merged blob of billions of stars, orbited by its smaller satellite galaxies in a quiet gravitational halo. And that island, that one bright, complicated mass of stars and gas and dark matter, will be what remains when the rest of the universe has gone dark. The Virgo supercluster's other member groups, the thousands of galaxy clusters beyond the local group, the Coma cluster and the Perseus cluster, and the tens of thousands of others catalogued by surveys across the sky, all of them will, over roughly 100 billion years, cross beyond the event horizon, redshift beyond detection, and vanish from any possible observation. Not destroyed, just unreachable. Just invisible, just gone from the sky as completely and as permanently as if they had never existed, as far as any observer within Milkomeda could ever know or verify. The local group, in other words, is an arc. Not an arc that saves its inhabitants from death. The stars will age and die on their own schedule. The universe will continue toward its own long-term fates. The physics of entropy will continue to do what physics does, but an arc in the epistemological sense, a vessel that carries forward into the far future, a community of mass and gravity and light. The last remaining context from which any observation will be possible, the last inhabited island in a universe that has otherwise placed all its other islands beyond the horizon. And even within that arc, there is a slow and gentle darkening already underway. The universe's rate of forming new stars has been declining for roughly 10 billion years. It peaked at what cosmologists call cosmic noon, a time corresponding to a redshift of approximately 2, meaning the universe was roughly 2 to 3 billion years old, when galaxies were colliding and merging with tremendous frequency, when gas was abundant and star formation was blazing at a rate many times higher than anything happening today. Since that peak, the universe has been on a long, slow exhale. The rate of new star formation has declined by perhaps a factor of 10 since cosmic noon. The gas that fuels star formation is being used up, and less is being replenished, and the overall luminosity of the universe, the total light output of all the galaxies combined, has been dropping. Slowly, but measurably. The universe is not yet dark. But the dimming, in the broadest sense, has already begun. So here we are. We have the cosmological constant, the force that is very close to nothing but never dilutes. The engine of exponential expansion that increasingly dominates the cosmos as everything else thins away. We have de Sitter geometry, the mathematical description of what a universe under that constant's rule looks like, a universe in which distances compound and the recession of unbound things accelerates without limit. We have the three horizons, the particle horizon at 46 billion light-years, the sphere of everything we can ever see, the event horizon at 16 billion light-years, the sphere of everything we can ever touch or be touched by, and the Hubble radius at 14 billion light-years, the surface where recession currently matches light speed, already crossed by most of what we observe. We have the near-nothing vacuum energy density of approximately 6 times 10 to the negative 27th kilograms per cubic meter, which sounds meaninglessly small until you remember that it never goes away, and so everything else eventually goes away relative to it. And we have the local group, our gravitationally bound family, our arc, our Milkomeda, to be, decoupled from the expansion and intact while the rest of the cosmos recedes past the horizon. With all of that machinery in place, slowly, gently humming in the background of the cosmos, the next question becomes the one that the story has been building toward since the beginning. What exactly vanishes? What are the clues that the future will not have? The universe has left us extraordinary evidence, evidence for how it began, evidence for how it has expanded, evidence written in the light of distant galaxies and in the faint microwave glow that fills every direction of the sky and in the precise ratios of light elements forged in the first 3 minutes after the Big Bang. These are not merely interesting facts, they are the scaffolding of our entire understanding of cosmic history. And every one of them, in the far future, will be gone. Not faded, not merely difficult, gone in ways that range from practically difficult to physically impossible, and the most important of those pillars will vanish, not because we lose the technology to see them, but because the physics of light and plasma and expanding space ensures that they cannot, even in principle, be observed anymore. That is where the story goes next, and it is where the cold center of this whole account lives, and it is worth arriving there slowly, with full understanding of the machinery that gets us there, so that when the pillars fall, one, and then another, and then the last, the weight of each collapse can be fully felt. Because each one is not merely the loss of a data point. Each one is the loss of a window, a way of seeing, a kind of knowing that, once gone, is gone without even the memory of its absence remaining. The universe is exquisite at this. at removing the evidence, at cleaning up after itself so thoroughly that nothing betrays what was there. Lie still and breathe and listen, because the next part of the story is where the three great lights of our cosmological understanding begin, one by one, to go out. And it starts with the simplest one, the most obvious one, the one you might think would last the longest, the one whose loss seems most straightforwardly explained, but whose implications run deeper than they first appear. It starts with the galaxies themselves and the specific thing their light was always telling us, and what it means that one day, in 100 billion years, give or take a few tens of billions, there will be no light from outside Milkomeda left to tell us anything at all. So let us begin with the one exception. In the whole expanse of what we can see, among the hundreds of billions of galaxies that populate the observable universe, the overwhelming majority are moving away from us. The space between us and them is growing. Their light is stretched red. The further they are, the faster they recede, and the farthest ones are already beyond any hope of contact, already ghosts in the most literal available sense. This is the universe's dominant motion, the Hubble flow, the relentless outward drift of everything from everything, and it is easy to fall into the assumption that it applies uniformly, that every galaxy without exception is carried along in the same direction, outward, always outward, like leaves floating away on a river that has no banks. But there is one large galaxy that is not doing this. One. In the whole sky, one large galaxy is moving toward us rather than away. And it is not moving toward us slowly or tentatively or by any small margin. It is approaching at roughly 110 kilometers per second. That is 110 kilometers every single second, which comes to about 396,000 kilometers per hour. Which is fast enough that if you could watch it from some impossible vantage point outside the local group, you would see it visibly closing the distance over geological timescales. You know its name. Almost everyone has heard its name. It is Andromeda, the Andromeda Galaxy, designated M31 in the catalogue that Charles Messier compiled in the 18th century to stop himself from confusing fuzzy permanent objects with comets. Messier found it a nuisance. We find it something else entirely. Andromeda is blue-shifted. That is the technical description, and it means almost the opposite of redshift. Where redshift tells us that a source of light is moving away and its waves are being stretched toward the longer, redder end of the spectrum, blueshift tells us that the source is moving toward us, compressing its waves, pushing them toward the shorter, bluer end. Andromeda's light is fractionally, measurably bluer than it would be if it were standing still. The blueshift is small because 110 kilometers per second is fast by human standards and modest by cosmic ones, but it is there, and it is unambiguous, and it is the fingerprint of approach. The reason Andromeda is approaching, rather than receding with the rest, is exactly the reason we have already spent some time with: gravity. Andromeda and the Milky Way are gravitationally bound to each other and to the rest of the local group, and that binding is strong enough to overcome the expansion of the space between them. The Hubble flow is a property of the unbound universe, the vast distances between galaxy clusters that have no gravitational attachment to one another. Within a bound system, the Hubble flow does not apply in any practical sense. The members of the local group are not being carried apart. They are in each other's gravitational embrace, orbiting around a common center of mass. And Andromeda's current trajectory brings it toward us rather than away. not because of any cosmic drama, but simply because of where it happens to be in its orbit around that shared gravitational center. This is the one companion we get to keep when everything else is gone. And it will not remain a companion at a distance. In somewhere between 4 and 4.5 billion years, Andromeda and the Milky Way will begin to collide. That word, collide, deserves some careful unpacking, because it carries with it a set of intuitions from everyday physical experience that do not quite apply at galactic scales. When you imagine two galaxies colliding, you might picture something like two boulders shattering each other, or two clouds of gas compressing violently into a single dense mass. But galaxies are mostly empty space. The stars within them are separated by such enormous distances that the actual likelihood of any individual star striking another star during a galactic collision is extraordinarily small. What happens instead is something stranger and, in its own way, more beautiful. The two galaxies pass through each other, or rather their gravitational fields pass through each other, pulling stars into new orbits, distorting the spiral arms, drawing out long tidal tails of stars and gas that arc through space like slow-motion streamers. The collision is gravitational and structural, not kinetic and destructive in the way a collision between two solid objects would be. There will be bursts of star formation as the gas clouds within the two galaxies are compressed together, and those bursts will light the merged system in new ways for a time. But the structure of the Milky Way as we know it, the elegant barred spiral that we live inside, will be dissolved. The structure of Andromeda, another spiral galaxy, will be dissolved alongside it. What will emerge over the following few billion years is something different from either predecessor. Astronomers call the anticipated result Milkomeda, a portmanteau that blends the two names into a single word for a single thing that does not yet exist. Sometimes it is also called Milkdromeda, depending on who is writing. The general picture is the same, a merged elliptical galaxy, lacking the flat disk and spiral arms of its parents, rounder, smoother, containing the stars of both the Milky Way and Andromeda, settled into new orbits around a shared center. If there is anyone still here to see it, and there is no particular reason to think there won't be, the night sky of Earth in those distant billions of years will look very different from the one we see now. Andromeda is already visible to the naked eye on a dark night, a faint smudge in the constellation Perseus, the largest apparent object in the sky other than the Milky Way itself. As it approaches over the coming billions of years, it will grow in apparent size. Eventually, it will dominate the sky. A vast tilted disk of hundreds of billions of stars stretched across a huge arc of the night, a second Milky Way crossing the first, and then the two dissolving into each other. A period of extraordinary visual drama unfolding over timescales no individual life can perceive, but that the geological record might one day carry a trace of. The Triangulum Galaxy, M33, the third significant member of the local group, will likely be absorbed into this merger as well, along with the dozens of smaller satellite galaxies that orbit both the Milky Way and Andromeda. The Magellanic Clouds, the large and small which are satellites of our own galaxy, currently visible in the southern sky as detached pieces of the Milky Way's glow, will over vast timescales be incorporated into Milkomeda. The whole local group, all of its 80-odd known members, will eventually coalesce, drawn by gravity, settling into a single merged structure, an island unto itself. And that island is all that will remain. Not because anything destroys the other galaxies. They will still exist, still burning with their stars. still harboring their planets, still doing everything galaxies do. But they will have passed beyond the horizon. They will have been carried by the expansion of space to distances from which their light can never, in all the remaining time the universe has, reach us. They will be cut off as completely as if they did not exist, because for every practical and every theoretical purpose, to us and to everything within Milkomeda, they will not. The information they might send will never arrive. The light they emit will never complete the journey. They will be as absent as if they had never been there, and in the end that is a kind of absence that is functionally indistinguishable from non-existence. This is the moment from which the three great losses follow. The first of them is the one you might expect, and it is also the deepest one, the one whose implications run through everything else. It is the loss of the redshift-distance relation. And to feel the weight of that loss properly, it helps to sit with what that relation actually is, and why it was such an extraordinary thing to discover, and what it gave us the moment we understood it. Imagine standing on a featureless plain at night, in perfect darkness, unable to see anything except a single point of light somewhere ahead of you. You want to know how far away that light is. Without anything else to go on, without any other visual cues, there is no way to tell from the light itself whether the source is a candle 5 meters away or a bonfire 5 kilometers away. Distance and brightness are entangled. A faint light could be dim because it is intrinsically faint, or it could be dim because it is far away and the distance has diluted its brightness. Without knowing one, you cannot determine the other. But suppose someone hands you a tool that can measure the color of the light, and suppose you know from theory and experiment that this particular kind of light source always emits a specific set of colors, always produces light at a fixed set of wavelengths, like a signature. Now you can compare the wavelengths you receive with the wavelengths you expect, and if they are shifted. If the received light is redder than the emitted light, you can calculate by exactly how much the space between you and the source has stretched while the light was traveling. And from that stretching, from that ratio between what was emitted and what arrived, you can derive the distance. The redshift is the distance. They are the same thing, expressed differently. This is what Edwin Hubble and his predecessors gave us. Hubble, working at Mount Wilson in the 1920s, built on Vesto Slipher's earlier measurements of galaxy velocities and on Georges Lemaitre's 1927 theoretical prediction, and found that the galaxies were receding at speeds proportional to their distances. The further they were, the faster they were moving away. This relationship, Hubble's law, gave cosmologists a ruler for the universe. Not a physical ruler, not a tape measure you could stretch between galaxies, but a mathematical one. Measure the redshift, get the recession speed, infer the distance. Suddenly the universe, which had been an undifferentiated fog of unknown depth, acquired a third dimension. It became mappable. The Hubble constant, that number around 70 kilometers per second per megaparsec that we have spent some time with already, is the slope of that relationship, the number that converts redshift into distance, that turns the color of light into a measurement of cosmic scale. This is one of the most powerful tools human science has ever developed. It allowed us to measure not just the distances to nearby galaxies, but the geometry of the entire visible universe, to trace back the expansion to its beginning, to calculate the age of the cosmos with reasonable precision, to understand the history of cosmic structure from the first moments after the Big Bang to the sprawling filaments and voids and superclusters of the universe we inhabit now. The redshift-distance relation is not a minor convenience. It is the foundation upon which modern cosmology rests. Without it, we would have no reliable way to measure the scale of the universe at all. In roughly 100 billion years, future astronomers within Milkomeda will have lost it completely. Not because they forgot it, or because their telescopes broke, or because some catastrophe destroyed their records, but because there will be nothing left outside their own galaxy to measure. The redshift-distance relation requires external galaxies, galaxies that are being carried away by the Hubble flow, galaxies whose recession can be measured and compared against their distance to be meaningful. If every external galaxy has slipped beyond the event horizon, if every source of external light has been cut off by the expanding space between us and them, then there is nothing against which to apply the ruler. The ruler still exists in some abstract mathematical sense, but there is nothing to measure with it, because everything that could be measured is gone. The future astronomer looking up from Milkomeda will see stars. Many billions of stars, the combined stellar population of the Milky Way and Andromeda and the rest of the local group, all orbiting within the gravitational embrace of their merged home. They will see the structure of their galaxy, its distribution of stars and gas and dust, its center and its outskirts. But beyond that structure, in every direction, they will see nothing. Not the faint smudge of a distant galaxy, not the streak of light from a far cluster. Nothing, perfect, absolute black, in every direction beyond the boundary of their own island. And so they will have no way to measure the expansion of the universe, because they will have no external objects that are expanding away from them. The very observation that founded modern cosmology, the observation that things far away are redshifted in proportion to their distance, will be physically unavailable. The Hubble flow will still exist. The universe will still be expanding, still driven by the dark energy that has never stopped its work. But expansion is only measurable in relation to something external, and in the absence of any external reference, there is no measurement to be made. The universe will be expanding, silently, secretly, with no witness who can tell. Hold that thought for a moment, because the second pillar is in some ways even more remarkable. The second loss, the second window closing, involves light that is not produced by any star or galaxy, but that is, in a sense, the afterglow of everything. It is the cosmic microwave background, and it is perhaps the most extraordinary single observation in the history of science, and what happens to it in the far future is specific and strange and worth understanding in its full detail. When the universe was very young, when it was a few 100,000 years old, rather than the 13.5 billion years old it is now, it was hot enough and dense enough that matter existed as a plasma. A plasma is a state of matter in which electrons have been stripped away from atomic nuclei by heat, leaving a soup of free charged particles. In that early plasma, light could not travel freely. Photons, the particles of light, were constantly being absorbed and re-emitted by the free electrons, scattered this way and that, unable to move more than a short distance before interacting again. The early universe was, in this sense, opaque. Light was trapped, bouncing around in the plasma fog, unable to escape. But the universe was cooling as it expanded, and at around 380,000 years after the Big Bang, it cooled to the point where electrons could combine with atomic nuclei and form neutral atoms, mostly hydrogen and helium, for the first time. This moment is called recombination. The moment the electrons joined the nuclei and the plasma became neutral gas, the fog lifted. Light was no longer being scattered by free electrons at every step. The photons that had been trapped in the plasma soup were suddenly free to travel across space, and they set off in all directions, and those photons are still traveling today. They have been traveling for approximately 13.8 billion years. In that time, the universe has expanded by a factor of about 1100, and their wavelengths have been stretched by that same factor. When they were emitted at recombination, they were the wavelengths of visible or near-infrared light, because the universe at 380,000 years old was still very hot, around 3000 Kelvin, glowing orange-white. After 13.8 billion years of expansion, those wavelengths have been stretched by a factor of 1100, pushing them far out of the visible range and into the microwave regime. The temperature of this bath of ancient light, as measured today, is 2.725 Kelvin, just a few degrees above absolute zero, and it fills the entire sky uniformly in all directions, an almost perfectly smooth whisper of thermal radiation arriving from every corner of the cosmos simultaneously. This is the cosmic microwave background. This is the imprint of the moment the universe first became transparent. When scientists first detected it accidentally in 1965, they were puzzled by the excess noise in their microwave antenna, a persistent hiss that would not go away no matter which direction they pointed it, and it took some time to understand that they were hearing, quite literally, the echo of the Big Bang, the afterglow of the earliest light the universe ever set free. Since then, it has been mapped in extraordinary detail by satellites, including the Planck Observatory, and its tiny temperature fluctuations, variations of a few parts in 100,000 from one patch of sky to another, have told us an enormous amount about the early universe, about the seeds from which all the large-scale structure of the cosmos grew, about the geometry and composition of the universe as a whole. The CMB is the oldest light we can detect. It is, in a specific sense, the wall at the back of the observable universe. We cannot see behind it, because the universe before recombination was opaque. The CMB is the last scattering surface, the earliest emission we can, in principle, ever observe with light-based instruments. It is the foundation of observational cosmology just as much as the redshift-distance relation is. Without it, we lose almost everything we know about the early universe. Now think about what happens to it as the universe continues to expand. Those microwave photons, already stretched from visible light into microwaves, are still being stretched. The universe is still expanding, driven by dark energy, and every year that passes sees those wavelengths grow a little longer. The expansion is exponential, not linear, so the rate of stretching is not constant, but accelerating. Over vast timescales, the wavelengths of the CMB photons will be pushed further and further toward the long end of the electromagnetic spectrum. They will be stretched from microwaves into radio waves, and from radio waves into ever longer wavelengths until they are kilometers long, and then longer than that, growing without any obvious stopping point. You might think this means they simply become harder and harder to detect, requiring ever larger radio telescopes, ever more sensitive instruments. That is true, but it is not the most interesting part of what happens. The most interesting part involves a property of space itself, specifically a property of the ionized gas that occupies the spaces between and within galaxies, the interstellar and intergalactic plasma. Any electrically conducting medium, whether it is the copper in a wire or the free electrons in a plasma, has what is called a plasma frequency. This is a characteristic frequency below which electromagnetic waves simply cannot propagate through the medium. It is not that the waves are attenuated or absorbed and weakened before eventually getting through. It is that below the plasma frequency, the free electrons in the medium respond to the incoming electromagnetic wave in such a way that they collectively cancel it out. The wave attempts to travel, the electrons respond, and the result is that no wave passes. This is not a technical limitation of detection equipment. It is a physical law of how electromagnetic radiation interacts with charged particles. Lawrence Krauss and Robert Scherrer pointed this out in their 2008 paper with a directness that, once you understand it, is genuinely unsettling. The CMB, as it is stretched to ever longer wavelengths over cosmic timescales, will eventually be stretched beyond the plasma frequency of the ionized gas that fills the universe. And when that happens, the CMB will not merely be too weak to detect with available instruments. It will be physically unable to propagate through the medium. The waves will reach the plasma and stop. Not be absorbed, not be scattered, simply fail to travel. The CMB will be cut off as completely as if the universe had a wall around it, and from within that wall there will be no signal. It is worth pausing on the distinction between difficult and impossible, because that distinction is the entire point. Difficult means you need a bigger telescope, a more sensitive detector, more time, more patience, more resources. Every generation of astronomers has had access to better instruments than the last, and that trend, in principle, continues. A challenge that is merely difficult could be solved by future civilization with sufficiently advanced technology, given enough time and ingenuity. But physically impossible means the laws of physics prevent it, regardless of technology. Regardless of intelligence, regardless of how patient or ingenious the observer might be. If the wave cannot propagate through the medium, then no telescope, however advanced, can detect a wave that never arrived. The photons do not exist as propagating waves in that regime. There is nothing to detect. The CMB's disappearance, when it comes, will not be a fading signal gradually swallowed by instrumental noise. It will be, from the perspective of the future observer, simply nothing. The afterglow of the Big Bang will not have been there for as long as anyone within Milkomeda can remember, and the notion that such a thing ever existed, a uniform thermal glow filling the sky from every direction simultaneously, a relic of a primordial fireball 13.5 billion years before the present, will seem like an extraordinary and unsupported claim. Because there will be no evidence for it. Not weakened evidence, not evidence requiring interpretation. No evidence at all, of any kind, detectable by any means available to physics. This is what Krauss and Scherrer mean when they describe the end of cosmology. It is not a dramatic destruction, it is a quiet erasure, the universe removing its own fingerprints. Let that thought settle, because the third pillar falls next, and the third one is, in its way, the strangest, because it involves the very atoms that make up the stars and the planets and the bodies of living creatures. And a question about where those atoms came from and how future observers will get that question profoundly, inexorably wrong. Most of the ordinary matter in the universe, the familiar baryonic matter that makes up stars and planets and everything we can see and touch, is hydrogen, the simplest element, a single proton with a single electron. Most of the rest is helium, the second simplest element, a nucleus of 2 protons and 2 neutrons surrounded by 2 electrons. Everything else, all the carbon and nitrogen and oxygen and iron and every other element in the periodic table, makes up a small fraction of the whole, produced by nuclear fusion in the cores of stars and distributed into space when those stars die. The universe, in terms of ordinary matter, is overwhelmingly a hydrogen and helium universe. Now here is the question that becomes crucial in the far future. Where did the helium come from? Some of it was made in stars. Stars are essentially controlled nuclear fusion reactions, and the most basic thing a star does is fuse hydrogen into helium. 4 hydrogen nuclei go in, 1 helium nucleus comes out, along with a burst of energy that sustains the star's luminosity. Every star does this. The Sun does it right now, generating roughly 4 million metric tons of helium per second in its core, and every star that has ever lived and died has done the same. Helium is constantly being made in stellar cores. But here is the thing, and this is the piece that Krauss and Scherrer identify as the third vanishing pillar. The universe began with helium already present. Long before the first star formed, in the first few minutes after the Big Bang, when the universe was dense and hot enough for nuclear reactions to proceed spontaneously, helium was forged directly from the raw hydrogen plasma. This is called Big Bang Nucleosynthesis, and it happened in a very precise way. The physics of that early fireball, the temperature and density and the rates of various nuclear reactions produced a very specific ratio of hydrogen to helium. Approximately 25% of the total ordinary matter, by mass, ended up as helium-4, the most common form of helium, with 2 protons and 2 neutrons. The remaining 75% stayed as hydrogen, with smaller amounts of deuterium and helium-3 and lithium-7 also produced in precise quantities that depend on the conditions in those first 3 minutes. This ratio, 25% helium by mass, is one of the clearest signatures of the Big Bang that we have. It is not the ratio you would expect from stellar production alone. Stars have been making helium for billions of years, but when you add up all the helium produced by all the stars that have ever lived, it does not account for all the helium in the universe. There is too much of it, more than stellar nucleosynthesis can explain. The excess helium, the helium that was there before any star formed, is the fingerprint of Big Bang nucleosynthesis. It is evidence that the universe had a hot, dense origin, that there was a moment early in its history when nuclear reactions proceeded in the open, expanding fireball of the cosmos itself, rather than in the enclosed cores of stars. Measuring this ratio, measuring the primordial helium abundance, and comparing it against the predictions of Big Bang nucleosynthesis, is one of the observational confirmations of the standard cosmological model. It tells us something specific about the conditions in the very early universe. It is a message written into the composition of matter itself, a message that has been preserved through billions of years of stellar activity because, while stars add helium to the universe, they do not add it in a way that would erase the primordial signal, at least not yet. But over sufficiently long timescales, they do. In 100 billion years, the universe will have been manufacturing stars for far longer than it has now. Generation after generation of stars will have formed, burned through their hydrogen, converted it to helium and heavier elements, died, and scattered their processed material back into the interstellar gas. The ratio of hydrogen to helium in a future galaxy will not be 75 to 25, the primordial ratio. It will be something different, shifted by billions of years of stellar nucleosynthesis. The helium fraction will be higher. The precise primordial signature will be diluted and eventually overwhelmed by the accumulated product of stellar processing. A future astronomer attempting to measure the helium abundance of their galaxy and compare it against what Big Bang Nucleosynthesis predicts will find that the numbers do not work the way we find them working today. The excess helium that now signals a primordial origin will be gone, absorbed into the general background of stellarly processed material. The future observer, measuring the composition of their galaxy's gas, will find a helium fraction that is consistent with purely stellar production, with no excess that requires explanation. They will see no trace of the primordial ratio, and they will therefore have no reason to suspect that any such ratio ever existed. That helium was once produced in the open fireball of the cosmos before the first star ever formed, that the universe had a beginning in which nuclear physics operated at scales we can barely imagine. Big Bang Nucleosynthesis is the last of the three pillars, and its erasure is perhaps the most intimate, because it is written into matter, into the very stuff of which we are made. And in the future, it will have been overwritten by the accumulated history of stellar physics, quietly, without announcement, the way any record erodes under the accumulation of time and subsequent events. So here they are, the three, the redshift-distance relation. Gone, because there are no external galaxies left to show recession. No sources of light outside Milkomeda against which to measure the expansion of space, no evidence that the universe contains anything beyond the single merged island that the future observer calls home. The cosmic microwave background, gone. Because the wavelengths of those ancient photons have been stretched so far by the expansion of space that they fall below the plasma frequency of the ionized medium. And below that frequency, they simply cannot propagate, cannot travel, cannot arrive. The afterglow of the Big Bang will be undetectable, not because it is too faint, but because the physics of wave propagation in a plasma does not permit it to exist as a traveling wave at those wavelengths. The observation that gave us our most detailed picture of the early universe will be as physically unavailable to the future observer as a sound wave is to someone floating in vacuum, and the primordial helium abundance. Gone, or rather buried, overwritten by the accumulated output of billions of years of stellar fusion, the original signal diluted below any ability to recover it. The fingerprint of Big Bang nucleosynthesis, indistinguishable from the routine product of ordinary stars, offering no evidence of any extraordinary event in the universe's past. Three pillars, three ways of seeing, three forms of knowing that we currently take entirely for granted, that we assume will always be there because they are so fundamental to how we understand the cosmos, that we have built entire branches of physics and astronomy around, that have given us essentially everything we know about the origin and history and large-scale structure of the universe. All three will be gone. Not degraded, not difficult to measure. Gone, and here is the thing that Krauss and Scherrer sit with in their 2008 paper, and that deserves to be sat with slowly. Because the loss of the three pillars does not merely leave the future observer in ignorance, it leaves them in a very specific and coherent picture of the universe, a picture that makes complete internal sense. A picture that requires no anomalies, no unsolved puzzles, no uncomfortable excesses that demand explanation. The future observer, having measured their galaxy as carefully as we measure ours, having applied every tool of scientific method with the same rigor and precision that our best scientists bring to their work, will arrive at a conclusion that is clean and consistent and well supported by all available evidence. They will conclude that the universe is a single large static island of stars in an infinite and otherwise empty void. That it has always been this way. That it will always be this way. That there is no expansion, no Big Bang, no cosmic history stretching back 13.5 billion years. No beginning, no primordial fireball. Just the one galaxy, permanent and eternal, surrounded by nothing. And they will be right, in the sense that their evidence fully supports that conclusion. Their logic will be valid, their measurements will be accurate, their science will be sound. The conclusion will be wrong, but there will be no way to know that from within the information available to them. The universe will have erased its own history so thoroughly that the correct reading of the remaining evidence points to a history that never happened. This is the ending toward which the whole story has been building. But before arriving fully there, before sitting with what it means and what it might mean for us, there is one more thing worth understanding. Because the sheer scale of this erasure, the completeness of it, the way the universe manages to remove not just one, but all of the independent lines of evidence for its true nature, raises a question that might not be immediately obvious, but that the quiet of this moment is good for. The question is not about the future. It is about the past. Because there is a reason we know all of this. There is a reason we can sit here in our brief moment in our 13.8 billion-year-old universe and describe in detail the mechanism by which the evidence is going to disappear. There is a reason we can look at the sky and see the CMB and measure the Hubble flow and determine the primordial helium abundance and use all of these instruments together to reconstruct the history of the cosmos from its first 3 minutes to its last observable era. There is a reason the universe is, at this particular moment in its history, still legible. And that reason is simply that we are early. Not early in any personal or human sense, not early relative to the Sun, which has roughly another 5 billion years before it swells into a red giant and becomes something unrecognizable. Not early relative to the Earth, which has existed for 4.5 billion years and, absent some external catastrophe, could persist for billions more. But early relative to the universe's full timeline in a way that is almost absurd when you look at the numbers. The universe is approximately 13.8 billion years old. The stars that currently exist, the main sequence stars burning hydrogen in their cores, will continue to exist for timescales vastly longer than that. Fred Adams and Gregory Laughlin, writing in a 1997 paper called A Dying Universe in Reviews of Modern Physics, laid out the full timeline of cosmic evolution in detail. They divided the future of the universe into eras named by the relevant physics of each. The current era, the stelliferous era, the era of star shining, extends from roughly now to approximately 100 trillion years in the future. 100 trillion. The number that is relevant to us, the 100 billion-year timescale for the disappearance of all external galaxies, arrives well within the stelliferous era. The stars within Milky will still be burning when the last external galaxy slips below the horizon. The universe will not be cold or dark in any absolute sense when the evidence disappears. It will just be lonely. And after the stelliferous era comes the degenerate era, when the remaining mass consists of white dwarfs and neutron stars slowly cooling in the dark. And after that, the black hole era, when even those remnants have decayed and only black holes remain, slowly evaporating through Hawking radiation on timescales that reach toward 10 to the power of 100 years. And after that, the dark era, when even the black holes are gone and what remains is a diffuse and almost infinitely dilute gas of the fundamental particles of physics, a universe so empty and so cold and so spread out that no structure of any kind can persist. Relative to those later eras, 13.8 billion years is nothing. It is an instant. It is the first breath of a very long sleep. If you were to map the entire future of the universe onto a single calendar year, we would currently be somewhere in the first few seconds of January 1st. And yet, in those first few seconds, we can see everything. We can see the CMB and deduce the universe's temperature when it was 380,000 years old. We can measure the redshifts of hundreds of billions of galaxies and reconstruct the expansion history of the cosmos with precision. We can analyze the helium fraction in the most pristine gas clouds we can find and read the signature of Big Bang Nucleosynthesis written there, preserved from a time before the first star ever ignited. We can trace the large-scale structure of the universe across billions of light-years and watch the cosmic web of filaments and voids and clusters that formed from the tiny temperature fluctuations in that ancient CMB. We can see the Dwests image of Jade's GSZ 14-0, a galaxy at redshift approximately 14. Seen as it was just 290 million years after the Big Bang, a galaxy that existed when the universe was barely 2% of its current age, and we can hold that image and know that we are looking at something real, something that was there, something that the light of billions of years has carried faithfully to our detectors. None of this will be available to the observers who come after. Not in 100 billion years. Not in a trillion. The evidence has an expiration date, and that date is set not by any fragility in our instruments or our civilization, but by the physics of an accelerating universe. The expansion of space will carry the evidence away. The plasma frequency will stop the waves, the stellar processing will overwrite the ratio, and then the window will be closed permanently, with no possibility of reopening it. We happen to live before the window closes. That is what the phrase, the golden age of cosmology, actually means when you follow it to its end. It is not merely a description of the fact that our instruments are better than those of previous generations, though they are. It is not merely a celebration of recent discoveries, though the last century of cosmological discovery has been extraordinary beyond any reasonable expectation. It is a statement about time, about when we are, about the cosmic calendar. We live in the only era in which the universe is fully readable, in which the light that carries its history is still arriving, in which the CMB is still detectable, still bright enough relative to the plasma frequency cutoff that its waves propagate freely across the cosmos and arrive at our detectors, in which the primordial helium fraction is still distinguishable from the stellar contribution, in which the expansion of the universe is written clearly in the redshifts of hundreds of billions of galaxies visible in all directions. We are reading the book before its pages are torn out. And there is a twist here, a historical resonance, a precedent for exactly this situation that sits close enough in time to feel personal, and it is the final piece of the story that remains to be told. We have been here before. That is the thing that makes all of this land with a particular weight, a particular closeness, when you sit with it long enough. The error the future civilization will make, the honest and reasonable conclusion that the universe is one small eternal island of stars in a featureless void, is not an exotic mistake, not some strange pathology of a civilization less careful than ours. It is the same mistake we were making 100 years ago, not 1,000 years ago, not in antiquity, 100 years. Within living memory of people alive when the evidence that corrected it was first gathered. The window between that darkness and this light is embarrassingly, uncomfortably narrow, and the future will close it again. Spend a moment with 1920. The year itself is not the date of the error. The error had been running for decades. But 1920 is when the error was most formally, most publicly dramatized, when two careful astronomers stood before an audience at the Smithsonian Institution in Washington and argued, in good faith, with good evidence, about whether the Milky Way was the whole of the universe or just one island in a sea of islands. That debate is known now as the Shapley-Curtis Great Debate, and what strikes you about it, if you read the transcripts, is not how foolish either side sounds, it is how reasonable both sides sound. Harlow Shapley argued that the spiral nebulae, the fuzzy smears of light that peppered the sky and had puzzled astronomers for generations, were small structures within or near our own galaxy. He had good reasons. He had measured the Milky Way to be far larger than previously thought. He had data suggesting the nebulae were rotating in ways that implied they were small. He believed, on the basis of evidence he had honestly gathered and honestly interpreted, that the cosmos was essentially what you could see, a vast galaxy, ours, surrounded by a darkness that was simply empty. Heber Curtis argued the opposite. The spiral nebulae, he said, were distant island universes, entire galaxies in their own right, separated from us by gulfs of space so enormous that their light arrived looking like a smear because distance had compressed them. He had his own evidence. Certain novae in the nebulae appeared far too dim to be within the Milky Way. The recession velocities of the nebulae, measured by Vesto Slipher in the years before the debate, were strangely high, strangely systematic, strange in ways that hinted at something larger than local motion. And there it was, Slipher's measurements. Beginning around 1912 and continuing through that decade, Vesto Slipher had been sitting at the Lowell Observatory in Arizona and carefully measuring the spectra of spiral nebulae, looking at how the wavelengths of their light shifted compared to what you would expect from a stationary source. And what he found was that most of them were redshifted, dramatically redshifted. Not the small Doppler shifts of nearby stars orbiting within the galaxy, but large, systematic shifts in a single direction, as if something was carrying the nebulae away at speeds that had no precedent in anything astronomers had previously measured. He published his results. He presented them. Almost nobody knew what to do with them, because without knowing the distances to these objects, you could not say whether the recession was significant or trivial, local or cosmic. The Great Debate ended in 1920 without a resolution. The question of whether the spiral nebulae were inside or outside the Milky Way remained genuinely open, not because the scientists were careless, because they did not yet have the tool that could answer it. And then, 3 years later, in 1923, Edwin Hubble found the tool. The tool was a type of star called a Cepheid variable. Cepheid variables pulsate, brightening and dimming on a regular cycle, and crucially, the period of that cycle, how long it takes to go from bright to dim and back, is directly related to the star's true luminosity, how bright it actually is. A slow pulsing Cepheid is genuinely more luminous than a fast one. Henrietta Swan Leavitt had discovered this relationship in 1908 while studying Cepheids in the Magellanic Clouds, and what it gave astronomers was something almost miraculous, a standard candle you could identify by watching it blink. If you find a Cepheid variable, you measure its period, you look up the corresponding luminosity. You compare that to how bright it appears in the sky, and you calculate how far away it must be. The dimmer it looks, compared to its known luminosity, the farther it is. Hubble turned the 100-inch telescope on Mount Wilson toward the Andromeda Nebula in 1923 and began photographing it night after night, looking for variable stars in its outer regions. He found them. He found Cepheids. And when he measured their periods and calculated their distances, the number that came back was staggering. The Andromeda Nebula was not a small object near the edge of the Milky Way. It was roughly 1 million light-years away, well beyond any plausible boundary of our own galaxy, a distance so large it put the object unambiguously in a class by itself, in the territory Curtis had described. It was not a nebula. It was a galaxy. And if Andromeda was a galaxy, then all those other spiral smears in the sky were galaxies too. The Milky Way was not the universe. It was one of countless islands in a cosmos far larger than anyone had seriously reckoned. Hubble announced the result in 1925. The great debate ended not with a debate, but with a photograph and a calculation. The error that had persisted through the entire history of astronomy up to that moment, the belief that what we could see was what there was, dissolved in the light of a blinking star. Then, building on Slipher's earlier redshift work, and on a theoretical framework worked out by a Belgian priest and physicist named Georges Lemaitre in 1927, Hubble went further. Lemaitre had derived from Einstein's equations of general relativity that the universe should be expanding, that galaxies should recede from one another at speeds proportional to their distances. In 1929, Hubble published his observational confirmation of that relationship, the famous velocity-distance plot that established what we now call Hubble's law. The faster a galaxy is receding, the farther away it is. The relationship is linear. The expansion is real and measurable. The universe began from a hot, dense state and has been growing ever since. Within roughly the span of a decade, the human picture of the cosmos had gone from a single island galaxy in a static void to an expanding universe containing what would eventually be counted in the trillions of galaxies. It was perhaps the largest single revision of our understanding of reality that science has ever produced, and it happened not because previous generations were stupid, but because they did not have the right observation at the right time. The evidence, when it came, corrected everything. Now hold that. Hold the image of 1920 and the year 2120 gentimillioned. In 1920, the mistake was honest and the evidence was missing. The spiral nebulae existed. The Cepheids existed. The distances were real. The expansion was already happening. Every fact that would eventually overturn the island universe assumption was out there in the cosmos, waiting to be read. The problem was not that reality was hiding anything. The problem was that our instruments were not yet sensitive enough, not yet precise enough to reach the facts that were there. In 100 billion years, the problem will be entirely different. The facts will not be there. Not hidden, not waiting for a better telescope, not encoded in some subtle signal that a more advanced civilization might someday decode. Gone, the expansion of space will have carried them past a horizon from which no signal can ever return. The plasma will have absorbed and scattered the echoes into a noise floor that physics itself cannot penetrate. The stellar furnaces will have reprocessed the atomic record into a new configuration that erases the original entry. The evidence will not be hard to find. It will not exist. And what will remain will be one merged island galaxy drifting in a void. Milkomeda, we have already said, the product of the merger of the Milky Way and Andromeda. A collision that begins in roughly 4 to 4.5 billion years and plays out over several additional billions as the two galaxy scale systems interweave and settle into an elliptical shape. The dwarf galaxies of the local group will be folded in over time. Triangulum, the Magellanic Clouds, the dozens of smaller satellites, they will contribute their stars to the merged system. And then, gradually, on timescales of tens of billions of years, the larger Milkomeda will consolidate and the void around it will empty, and the merged group will be the only gravitationally bound structure within the observable universe of whoever lives there then. That civilization, if it exists, will be in the position of Harlow Shapley, with one difference that changes everything. Shapley was wrong, but the evidence to correct him was already in the universe, encoded in the periods of variable stars in a neighboring galaxy. Hubble could reach it. The future civilization will be wrong, and the evidence to correct them will not be in the universe. Hubble's method will not save them, because there will be no neighboring galaxies to point a telescope at, no Cepheids in external systems to measure. No external systems at all. They will search. They are rigorous. They are honest. They point their instruments at the darkness in every direction and measure nothing. Because there is nothing to measure. And they conclude, as any careful scientist would conclude, that the universe is simply this: one body of stars in a void. They will not have the great debate. They will not have two sides arguing island universe versus single cosmos, because every line of evidence that could generate the pro-expansion side of that argument will have been erased. The debate will not be unresolved. It will be prematurely and permanently resolved in favor of the wrong answer by the absence of evidence that once existed and was real, that we right now can read in the sky, that will not survive to be read by them. There is something specific about the helium that is worth dwelling on, because it is perhaps the least intuitive of the three erasures, and in some ways the most poignant. The universe made helium before it made anything else of note. In the first few minutes after the Big Bang, when the cosmos was a seething fireball hotter than any star that would ever form, protons and neutrons combined in a process called Big Bang Nucleosynthesis. The physics of that process, the temperature, the density, the ratio of protons to neutrons, the timescale over which things cooled below the threshold for nuclear reactions, produced a very specific outcome, roughly 75% hydrogen and 25% helium by mass, with traces of lithium and almost nothing else. That ratio is a fingerprint. It is a record encoded in the lightest nuclei of every atom forged in those first minutes, preserved in the primordial gas that eventually collapsed into the first galaxies and stars. Astronomers can measure that ratio today. They look at very old, very metal-poor stars, or at the spectra of ancient gas clouds, environments where stellar processing has had the least opportunity to alter the original composition, and they find the primordial helium fraction sitting there, roughly as predicted by the theory of Big Bang nucleosynthesis, roughly 25% by mass. That match between the theoretical prediction and the observed abundance is one of the great triumphs of modern cosmology. It tells us the Big Bang happened and that the early universe was exactly as hot and dense and well described by known physics as the model says. But every star that ever lived or lives now is a helium factory. Take hydrogen, collapse it under gravity, heat it to 10 million degrees, and you trigger nuclear fusion, which converts hydrogen to helium. Every star does this. Every star has done this. Billions of years of stellar processing across trillions of stars has been steadily adding helium to the cosmic inventory on top of the primordial 25%. Today, the stellar contribution is still relatively small compared to the primordial reservoir, and careful astronomers working in the right environments can still distinguish the original signal from the processed layer on top. In 100 billion years, generation after generation of stars will have lived and died and exhaled their processed material back into the galaxy. The helium fraction in the interstellar gas will have climbed well above 25%. Future astronomers, measuring the helium in their galaxy, will see a number that does not match the Big Bang Nucleosynthesis prediction. Not because the prediction was wrong, but because the prediction applies to the pristine primordial mix, and that pristine mix no longer exists in a readable form. They will conclude that stellar processes account for all the helium they observe. That is a perfectly reasonable conclusion from the evidence they have, and it will cause them to miss the most important cosmic event in history. The three pillars, each one an open door that will be bricked over. Each one a fact about the universe that is real and readable now. That we are genuinely lucky to be able to read, that will be gone. This is the shape of the argument that Lawrence Krauss and Robert Scherrer laid out in their 2008 paper in General Relativity and Gravitation, and what makes it remarkable is not that it is speculative. It is not speculative in the pejorative sense. It follows directly from the physics we know, from a cosmological constant with an equation of state parameter close to -1, from de Sitter expansion, from the plasma frequency of the interstellar medium, from the arithmetic of nucleosynthesis. If the cosmological constant stays roughly what it is, these things happen. The paper is not a wild extrapolation, it is the careful, somewhat grim working out of consequences. Before we settle into the quiet of the outro, one alternative scenario deserves a brief stop, flagged clearly as what it is, a possibility, not the expected fate. What if dark energy is not a true cosmological constant? What if the equation of state parameter W is not exactly -1, but is instead slightly more negative than that, below -1? Such a form of dark energy goes by the name phantom energy, a term coined by physicist Robert Caldwell and colleagues in a 2003 paper. Phantom energy has a peculiar property. Unlike the cosmological constant, whose density stays fixed as space expands, phantom energy's density actually increases as space expands. More expansion means more phantom energy, which means faster expansion, which means even more phantom energy in a runaway loop that ends not in a slow asymptotic darkening, but in a catastrophic tearing called the Big Rip. In a Big Rip scenario, the accelerating expansion eventually overcomes every bound force in nature, one by one, starting with the largest scales and working down. Galaxy clusters are torn apart first, then individual galaxies, then solar systems, then planets. Then, at the very end, in the final fractions of a second before the singularity, atoms themselves are ripped apart, nuclei pulled apart from electrons, protons and neutrons shredded into their constituent quarks. The universe ends not in a slow fade, but in a violent disintegration of everything that exists. The current observational data does not favor this outcome. The Planck satellite's measurements of the cosmological parameters put W at approximately -1.03, with an uncertainty of roughly plus or minus 0.03. -1 is comfortably inside that uncertainty. The data are consistent with a true cosmological constant, with no phantom behavior, no Big Rip. The mainstream expectation, the one that generates the 100 billion year darkening described in this video, is that W stays near -1. But the data cannot yet rule out phantom energy at every level of confidence, and Caldwell's scenario remains a genuine, if disfavored, alternative. It is worth knowing that it exists, worth knowing what it implies, and worth understanding that the main story, the quiet darkening, the slow crossing of galaxies past the horizon, the epistemic fading of all three pillars, is what the best current evidence points toward. The Big Rip would be worse in one sense and the same in another. Worse because it ends in destruction rather than isolation. The same because in either scenario, the evidence that tells you the true story of the cosmos disappears before any future civilization can read it. Whether it disappears over 100 billion years or over a shorter catastrophe, the epistemic loss is total. So we keep the main story, the quiet one, the one where everything stays intact, where our merged island galaxy drifts through an enlarging void, where Milky stars keep burning for trillions of years according to the timeline laid out by Fred Adams and Gregory Laughlin in their 1997 paper in Reviews of Modern Physics, where they tracked the future of the universe through what they called the stelliferous era, the age of stars, lasting from roughly now to about 10 to the power of 14 years. We are still early in that era. Very early. Absurdly early. Think about what that means, held as a number rather than an abstraction. The stelliferous era lasts roughly 100 trillion years. We are 13.5 billion years into the universe's life, which is to say roughly 13.5 billion out of 100 trillion years into just the starlit portion of cosmic history. That is about 1/10,000th of the stelliferous era. Not 1%, not 1/10 of 1%, 1/10,000th. After the stelliferous era ends, the universe enters the degenerate era, white dwarfs and neutron stars cooling over unimaginable spans, followed by the black hole era, where the remaining mass concentrations slowly evaporate via Hawking radiation over timescales stretching to 10 to the power of 100 years, followed by the dark era, in which essentially nothing of the organized universe remains. The full timeline of the cosmos, from now to its most remote imaginable future, dwarfs the stelliferous era the way the stelliferous era dwarfs the age of the universe so far. We are, by every measure, at the very beginning, the lightest sliver of the cosmic day, closer to the moment of creation than to anything that might be called cosmic middle age. The universe is young. We are young in it. And yet, in this youth, in this almost comically early position on the timeline, we find ourselves equipped with the exact instruments needed to read a story that will not survive, to be read by those who come after us in any meaningful cosmic sense. The CMB is bright enough to detect. The primordial helium is still discernible from stellar processing. The redshifts of hundreds of billions of external galaxies are still arriving at our detectors, encoding the full history of expansion in their stretched wavelengths. There is a deep, strange luck in this. Not the luck of survival, not the luck of circumstance in the everyday sense, but a cosmological coincidence that sits at an intersection of when life could have arisen and when the evidence was still readable. Complex life requires elements heavier than hydrogen and helium, elements that only form in stars and get distributed by supernovae and stellar winds into the interstellar medium from which new generations of solar systems form. You cannot have carbon-based biochemistry. You cannot have rocky planets with liquid water without at least a few generations of stellar processing. It takes time, billions of years. The universe had to cook long enough to make the ingredients, and yet it had to be early enough that the evidence was still there. Cosmic noon, the peak of star formation, happened about 10 billion years ago, when the universe was roughly 3 to 4 billion years old, at a redshift of approximately 2. Since then, the overall rate at which the universe converts gas into new stars has been declining, slowly, steadily, in a long dimming. We are already past the brightest moment of universal star formation. The universe has already made most of the stars it will ever make. In that sense, the lights have been dimming for 10 billion years already, long before any of the horizon crossing effects that Krauss and Scherrer describe. The physical darkening and the epistemic darkening are both already, in the slowest sense, underway, but 10 billion years from cosmic noon is not long enough for the evidence to disappear. The CMB is still here, the galaxies are still visible, the primordial ratio is still distinguishable. We arrived, as a species and as a civilization capable of asking cosmological questions, in the narrow zone where the ingredients for our existence had been assembled and the evidence of the universe's true nature had not yet been erased. That window is real. It is not infinite. It closes. And the closing is not a metaphor. It is not a poetic framing. It is the physics of an accelerating universe measured in the redshifts of type Ia supernovae by Saul Perlmutter and Brian Schmidt and Adam Rees in 1998, confirmed by the Planck satellite's mapping of the cosmic microwave background and the large-scale structure of the cosmos, written into every cosmological calculation we know how to do. The window closes. We happen to be born inside it. There is a question that sometimes surfaces at this point, a natural one, the kind that comes in the quiet after you have absorbed the shape of the argument. It is something like, does it matter? If the future civilization never learns the truth, if they live their entire existence in a universe that looks small and static and eternal, if they never know what they are missing, does it matter that they are wrong? That question lives in philosophy more than in physics, and this is not the place to answer it fully. But there is one thing worth saying about it, and it is this. We asked a version of it 100 years ago without knowing we were asking it. The astronomers who believed the Milky Way was the whole universe were not troubled by what they did not know, because they did not know it. The missing evidence did not announce itself as missing. The darkness between the stars did not announce itself as full of galaxies. Shapley held his island universe model not with the anxiety of someone who suspects they are wrong, but with the confidence of someone who has looked carefully and found nothing to contradict them. The absence felt like emptiness. And then Hubble found the Cepheids in Andromeda. And the absence turned out to have been full all along. The future civilization will never have their Hubble. That is the asymmetry. That is what changes the error from correctable to permanent. We had our darkness corrected. They will not. Which brings us at last all the way back to the beginning, to the place the script started, to the astronomer standing at the eyepiece of a telescope on a lone island galaxy in the far future, scanning a perfectly black sky and drawing the most reasonable conclusion the evidence permits. One universe. One galaxy. Static. Eternal. Small, in the sense that it has edges you can in principle trace, the edges of the merged local group, the merged Milkomeda, the small collection of dwarf systems that stayed bound. That astronomer is not a fool. that civilization is not incurious or lazy or philosophically impoverished. They are doing what we do. They are looking up. They are measuring. They are building theories from the data and testing those theories against new observations and refining them when discrepancies appear. They are, in every sense that matters to us, doing science. And their science will tell them, correctly, that they live in a small, static, eternal universe. The wrongness will not announce itself. It will not feel like wrongness from the inside. It will feel like knowledge. We know it is wrong because we happen to live in the window when the proof is still available. We know about the redshifts because Hubble published them in 1929, and every astronomer since has confirmed and extended his work. We know about the expansion because Lemaitre's equations predicted it and Hubble's observations confirmed it. We know about dark energy because Perlmutter and Schmidt and Rius noticed that their supernovae were too dim and followed that dimness to its astonishing conclusion, which earned them the 2011 Nobel Prize in Physics and fundamentally changed our picture of the universe's future. We know about the cosmic microwave background because Arno Penzias and Robert Wilson accidentally detected it in 1965, and subsequent missions, culminating in the Planck satellite and its 2018 data release, have mapped it with extraordinary precision, measuring its temperature at 2.725 Kelvin and extracting from its tiny fluctuations a nearly complete census of the universe's contents and history. We live in the golden age of cosmology. That phrase is used often and somewhat casually, but Krauss and Scherrer's paper gives it a precision it does not usually carry. It is not just that our instruments are good and our theories are refined and our data sets are richer than at any previous point in the history of science, though all of those things are true. It is that the evidence is available. The full set of facts needed to deduce the true nature of the universe, its origin, its composition, its history, its trajectory, is still encoded in observable signals that are still arriving at our detectors. The cosmic microwave background is here, still propagating freely, still above the plasma frequency cutoff, still measurable. The external galaxies are here, still inside the event horizon, still sending us photons redshifted in proportion to their distances, still telling us the expansion story in every spectrum we take. The primordial helium is here, still distinguishable in the oldest and most metal-poor environments we can identify, still matching the Big Bang Nucleosynthesis prediction closely enough that we can call it a confirmation. The golden age of cosmology ends not when our instruments get worse, or our funding runs out, or our civilization loses interest. It ends when the evidence expires. That is a different kind of ending, slower, more absolute, unreachable by any upgrade of technology or any increase in resources. It ends because the universe is moving the evidence away. And we are, right now, in the only era in which the book is complete, in which every chapter is still readable, in which a civilization that looks carefully enough can deduce the whole story. We are not the ignorant ones, stuck in darkness, waiting for a revelation. We are the privileged ones, the ones who happened to arrive while the library was open. The light is still here. The signals are still arriving, the supernovae are still exploding in distant galaxies, and their light is still reaching our telescopes and telling us, in the language of wavelength and intensity, that the universe is larger and stranger and more precisely structured than any pre-1925 astronomer could have dreamed. We are reading the book before its pages are torn out. That is what this is, not doom. Not an invitation to despair at the darkness that is coming. The darkness is coming, on timescales so long they resist imagination, and when it arrives it will be complete and permanent, and the civilizations that live inside it will never know what they missed. But we are not inside it. We are on the other side of it, in the bright side, in the window. The light is still here. The story is still legible. And maybe that is the thing worth taking with you. The thought worth carrying as you settle in for sleep tonight. Somewhere above you, right now, photons from a galaxy 1 billion light-years away are striking the upper atmosphere and scattering. Some of them absorbed by the air, some bouncing around until they dissipate. And somewhere in that stream of ancient light is information about the expansion of the universe, about the rate at which space stretched between here and there, about the size and shape of the cosmos that holds all of this, all of us, all of it. That information has been traveling for 1 billion years. It arrived tonight. And we are the kind of creatures at this particular moment in the history of a middle-aged star and a young civilization who can detect it, interpret it, understand it, and know that it will not always be here to be read. There is a particular quality to knowing that. A stillness, a feeling of the ground, of being placed, not frightened, not saddened, but located in time in a way that most creatures and most moments are not. We know when we are. We know the evidence has an expiration date. We know we are early enough in the cosmic story to have read the chapters that come before us, old enough as a civilization to have built the instruments to read them, and fortunate, in the plainest sense of that word, to have arrived when we did. The sky is slowly going dark, not tonight, not in any lifetime or any dynasty or any geological epoch. But it is going dark, on the cosmological timescale, in the deep future, one galaxy at a time crossing a horizon from which it cannot return. One echo fading below the plasma frequency, one atomic fingerprint overwritten by a star. The lights are going out, slowly, at the edges, and in the far future the last one will go, and a civilization that has never known any other sky will look up at the darkness and call it complete. We see it differently. We see it full. That thought, perhaps, is the kindest one to sleep on. Not the darkness, but the fullness of this moment. The improbable completeness of the sky above you as you close your eyes. Every direction you might look, if you could look through walls and atmosphere and daylight, there are galaxies. Hundreds of billions of them within our observable universe, each one a city of stars, each one receding with the expansion, each one still close enough and bright enough that its light arrives and tells us it is there. The universe above you tonight is not the truncated, silenced, horizon-bound future. It is the full, open, evidence-rich present. The pages are still there. The book is still open. If something in this video caught at something in you, some image or number or thought, something you will carry into tomorrow, I would love to hear what it was. You can leave it in a comment below, even just a few words, and it genuinely helps to know what lands. And if this kind of slow, careful exploration of the very large is something you want more of, there is always another class to sit in on. Close the books, dim the lamp. Class is over, sleepy scholar.